the universe. From the glowing wisps of nebula to the shine of newborn stars, from blazing galaxies to the warm embrace of our own sun, the universe has dazzled humanity for all time with its brilliance. However, the universe is mostly space, and that space is cold, very cold. But that doesn't mean there isn't anything to see. When observed in a special way, even cold things glow. Like these strangely colored blobs, they aren't exotic cosmic objects at all, nor will they ever fill a room with their light. Even these ice cubes emit radiation we can detect, infrared radiation. Infrared radiation is created by the motion of atoms and molecules that are in matter. So even objects that we think of as being very cold, such as ice cubes, emit radiation. Like ice cubes, the coldest things in space emit radiation. And with special instruments, we can detect this radiation to reveal a dazzling universe of unseen wonders. Legions of galaxies, and what lies within their cores. The secrets of seemingly empty space. The birthplace of stars. And even the birthplace of planets. Planets like ours. How do we see these things? With the Spitzer Space Telescope, the last of the 4 great observatories. Spitzer's greatness is not due to its size. With a mirror less than 3 feet across, it is easily dwarfed by the other great observatories, Hubble and Chandra. But despite its modest stature, Spitzer's infrared observations are 1,000 times more sensitive than any ever made. That's because it does its work in the frigid depths of space. Positioned in a unique orbit, 1,000,000 miles distant, Spitzer trails the Earth like a lone sentinel, following us as we journey around the Sun. Here, in the deep freeze of space, Spitzer is far from anything that would interfere with its infrared vision. By gazing into the distant reaches of space-time, or perhaps somewhere nearby in our own galaxy, photons are gathered by Spitzer's mirror. From here, the photons can be directed to different instruments that are frozen in liquid helium so they don't emit infrared radiation that would interfere with the observations. With a photometer, spectrometer, and cameras, observers can count, characterize, and make images with the infrared energy from sources, allowing us to see what has never been known. They can see stars that are invisible to our vision. They can sense vast, invisible clouds of matter and reveal what they're made of. They can reveal dust around stars, dust that is forming planets like ours. And they can detect galaxies in the deepest reaches of space-time.
Main engine start and liftoff of the Delta II.
Launched in August of 2003, Spitzer has completed its primary mission: to establish a legacy of new information about our universe, the Spitzer legacy. How do stars form? What causes them to form? How do solar systems form? Do all stars have solar systems? Are there any solar systems like ours? Are there many? Are there few? What does our galaxy really look like? Are new stars forming in our galaxy? Where? Why did galaxies form? Were the first galaxies like our galaxy? Why are galaxies where they are? How did the structure of the universe form? These are questions that the Spitzer Legacy Program is designed to address. Using Spitzer's unprecedented infrared vision, 6 programs focused on different aspects to fill gaps in our knowledge. 2 Spitzer Legacy programs were designed to understand the universe on the largest scales. They were GOODS and SWIRE.
GOODS stands for the Great Observatory's Origins Deep Survey. The origins part is a reference to our own origins. It's a search for the origins of galaxies and the components in galaxies, the constituent parts of galaxies, dust, gas, stars, how that material collected together and built up and gathered into the units that we call galaxies today. Where did those come from? How did they build up over time? We know what the local universe around us is. We know what our Milky Way is like. We know how massive it is. We know what its stars are like. We have some idea of how old it is. And we would like to know how it got to be that way. We know that the universe didn't always have galaxies like the Milky Way. At one time, it didn't have any galaxies at all. So how did we go from that early era where there was very little to a universe like today where we have big galaxies like the Milky Way? So we're searching for our origins using the Great Observatories. It's a deep survey, deep meaning both faint and also deep in the universe, to see great distances and far back in time. We can now see galaxies back 90% or more of the way back to the Big Bang, back to the beginning of time, and see some of the youngest and earliest galaxies known. It's like a core sample or an archaeological dig. We're digging down through the universe and seeing earlier and earlier eras by measuring the light from those galaxies at younger and younger times in the universe. And before Spitzer, there was really no facility that could see the light from the stars that dominate the mass of galaxies at these early times in the universe. There was really just no way to do it. From the ground, you can't see faint enough. The sky is too bright. You just can't see these galaxies. There's just no way. And no previous space mission had the capacity to do a deep survey like this. So Spitzer is giving us a chance to see, essentially to weigh distant galaxies, to measure the mass of stars in those galaxies by observing the light at wavelengths where the stars that contribute most to that mass radiate. That's one of the 2 major things. The other aspect that Spitzer allows us to study is the energy emitted by stars that are newly formed or by giant black holes inside those galaxies, what we call active galactic nuclei, the giant black holes that we now believe live at the center of most galaxies. The thing is, a lot of that energy gets absorbed by dust, whether it's from star formation or from these black holes. And it would be coming out at shorter wavelengths, ultraviolet wavelengths, but the gas and dust in these galaxies absorbs that light. And where does it come out? It has to come out somewhere. It comes out again re-radiated at these cooler temperatures and longer wavelengths, where Spitzer is the instrument of choice to observe it. And what we see is a process by which the galaxies were much smaller and much less massive at those early times, and they get more massive with time. So somehow we're trying to understand that process by which the galaxies have built up their material, built up their mass over the history of the universe.
SWIRE was the other survey that focused on what is, in a way, the largest story of the Spitzer Legacy Program. This infrared image made by the SWIRE survey contains over 500,000 brilliant, gleaming sources. Vast numbers of what first appeared to be pinpoints of light are entire galaxies, seemingly innumerable. By virtue of this wide coverage, Swire is helping to piece together one of the biggest subjects in astronomy: the large-scale structure of the universe and how galaxies evolved within that structure.
The primary goal for Swire is to understand galaxy evolution, and we decided we needed to look at large fields because we wanted to look at the evolution of different types of galaxies together in the same volume of space. We didn't want to zoom in on one kind of galaxy over here and a different kind of galaxy over there. And in particular, we wanted to trace those galaxies over the cosmic web. The cosmic web is the filaments and clusters and voids, the patterns of galaxies as we find them in the universe. They've been mapped very well in the local universe, but not so well in the distant universe at all. And so by taking Swire and looking deep into the universe in large patches of sky, we could actually see how things are forming at moderate distances away from the Earth. One of the key issues is that we don't understand the relationship between the cold dark matter that we suspect lies out there, tracing the major structures in space, and the way that the galaxies have formed within the concentrations of this dark matter. Now, cold dark matter is one of the strangest concepts we actually have. If you look up at the night sky, you see the stars shining brightly, and you think the universe is dominated by these wonderful points of light, and then the galaxies that are agglomerations of stars which shine brightly. But in fact, to our astonishment, we learned that only about 4% of the matter in the entire universe is actually visible, whether through the naked eye or the telescope. And in fact, astronomers believe that about 20% of the rest of the matter in the universe is what we call this cold dark matter, and it dominates the gravitational behavior of what we see, the galaxies, the light elements. And so we can look for the galaxies and we can trace out their structures on the sky, and that's what we're trying to do with Swire. And we're hoping that it will highlight the dark matter that lies underneath that we can't see. The way that Swire is going to study the evolution of galaxies is what we want to do is compare how the distant universe looks to the local universe. Astronomy has this fabulous aspect to it that we can use it as a time machine. Because light takes a finite amount of time to travel, the further away an object is, the further back in time you're actually looking back to see it at. And so if we just look across the solar system, we're looking at the distance of a few light hours. But if we look outside to the Andromeda Nebula, which is our nearest neighbor large spiral galaxy, that's about 2 million years. So we're seeing Andromeda as it was 2 million years ago. Now, if we just keep on looking further and further away back into the past of the universe, we can see how galaxies actually appeared a long time ago. We just look further away and there it is. And so Swire is looking back large distances, a range of distances, up to several billion light years ago, just by looking far enough away into our deep field images to see the galaxies how they looked before. So we will measure how they appeared in the past, and then we will compare them to objects that we know and love in our local universe. So the ultimate goal of Swire is to be able to map these structures out on the sky, delineated by the different galaxy types, and not only in 2 dimensions, that is a map on the sky of filaments and clusters and voids, but in 3 dimensions. And so we'll have a volume of the sky at these moderate to distant distances in the universe where we've actually mapped the distribution of the different types of galaxies. And ultimately, we hope to compare that to what is seen in the local universe in some of the large-scale surveys that have been done in recent years, such as the Sloan Digital Sky Survey, which has actually taken a huge amount of effort to map the entire northern hemisphere of the sky locally. We think of Swire as the Sloan of the higher redshift universe, and we'll be able to directly compare the structures seen at those higher redshifts in Swire to the local universe and see how they have changed in time.
2 other legacy programs, SINGS and GLIMPS, focused closer to home to understand our own galaxy and those in our cosmic neighborhood.
SINGS stands for Spitzer Infrared Nearby Galaxies Survey. And the idea of the survey is really to broadly sample the local population to get a census that is representative of all of the types that are found today in the universe, and also provide type examples for the kinds of things that surveys like Swire will see in the distant universe. Ours is actually a survey, as the name implies, nearby galaxies, They're within distances of about 100 million light years of the Milky Way. What that really means is our galactic neighborhood, galaxies within a local supercluster, and it includes a lot of the kinds of famous galaxies that many amateur astronomers will look at in their backyards. For example, the Whirlpool galaxy, M51. The advantage of looking at galaxies nearby is that we can actually make images and study in great detail the galaxies. In fact, many of the images that we're obtaining are some of the most beautiful images Spitzer is obtaining. In addition to effectively photographing the galaxies with the MIPS and IRAC instruments, we're also mapping the galaxies using the spectrometer on Spitzer, the IRS instrument. What those maps do provide us is physical information about the physical conditions in the star-forming regions. Things like the temperatures of the gas, the pressure of the gas, the motions of the gas. And this allows us to obtain hard numbers on the properties of the star-forming regions, and really allows us to pull that much more information out of the photographs and images that we obtain. The Whirlpool galaxy M51 provides an excellent example of the power of these infrared observations. If you look at an optical image, in other words, one made in visible light, you can see knots of star formation that are in the visible. You also see the image crisscrossed with dark lanes, dark features. These are dust lanes, clouds of gas and dust. And in truth, the stars really are being born at this time in those dark lanes, but most of that star formation is nearly utterly invisible to us from the ground because that dust is obscuring those regions. It's the same gas and dust that was giving birth to the stars also provides a cloak that hides those regions from us. Now, if you look at the same galaxy in the Spitzer images, you in fact see that what were dark lanes in the visible image are now bright. That Spitzer actually is measuring the light from that dust, and suddenly you can see a series of knots of these truly newly born stars that were not visible in the optical photograph. Of course, neither of these pictures is complete, but by combining the view from the visible with the view from the infrared, we get a complete picture of the star formation. And this is something that Spitzer is doing for the first time. It is not the first telescope to study galaxies like the Whirlpool in the infrared, but it has unprecedented ability to make sharp images of these galaxies in the part of the infrared spectrum where most of these young stars are producing their light.
Glimpse looks even closer to home and promises to deliver much more than its name implies.
The anagram itself is the Galactic Infrared Midplane Survey Extraordinaire. And we believe, in fact, that it is extraordinary in the sense that we're seeing an entirely new view of our galaxy that really nobody has seen before. We see a whole range of different kinds of objects. We're also uncovering many, many more stars than essentially any other survey has done for this particular area. As, we've uncovered something like 50 million stars that will be cataloged. So we're seeing about 50 times more stars per unit area.
And what is revealed? This first look from Glimpse sees all the way to the far side of the galaxy. Except for a few bright stars, nothing in this picture would be seen in visible light. It would be darkness. But with Spitzer, our galaxy is revealed anew as never seen before. It shows millions of stars, 50 times more stars than we've seen before in any light. But it is still less than 10% of what Glimpse looks at. This tiny sliver of that vision contains a treasure trove of new objects and volumes of information about our Milky Way. With millions upon millions of new stars to observe with this new vision, GLIMPSE will help address one of the vexing questions in astrophysics.
Well, believe it or not, the galaxy is full of stars. It's got about 100 billion stars. But in fact, nobody really understands how these stars are made. It's one of the great mysteries of modern astrophysics. And we have the hope that with the GLIMPSE data, we can in fact understand some of the process by which stars are made. There's a very complicated physics that's involved, and that's something that nobody's been able to do really in any direct way from observations, but I think GLIMPSE will be able to do that.
2 legacy programs were designed to understand the evolution of stars and planets. One was given the name C2D.
C2D stands for cores to disks, and to understand what I mean by that, I need to back up a little bit and describe how we think stars and planets form. The stars and planets form out of the material between the stars, what we call interstellar space. And the immediate problem you come to is that stars are a lot denser than the material in interstellar space. A typical star like the Sun has an average density about like water. So if I took a box about the size of a sugar cube, I'd have about 10 to the 24th power particles in that box for an average piece of the Sun. And if I took an average part of interstellar space, I'd have about 1 particle in there. So we're talking about a huge increase in density, which can only be achieved by taking a big volume and a lot of matter, therefore, at low density and shrinking it down. So the places where this happens are called molecular clouds. So they are relatively denser regions. They may be 100 to 1,000 times denser than the general interstellar space. And they're composed primarily of molecules and dust. And so within these clouds, there are particularly even denser regions, still very low density compared to what we need, but maybe 10,000 times the average interstellar medium. And those are called cores. They are sort of condensed regions within the clouds, and those are the places where we think stars either will form or are forming now. So that's the cores part of cores to disks. Now, as these cores collapse to form stars, if they have even a little bit of initial rotation, they will begin to spin faster as material falls in. This is exactly the same thing that happens when an ice skater goes into a spin, pulls her arms in, and actually speeds up. It's due to the conservation of angular momentum. So as these things collapse, as this material falls in to become a star, some of it actually doesn't fall into the star. In fact, most of it falls into a disk-like structure around the star. And the star grows from material going through the disk and go onto the star. But what's really interesting is what's left in the disk, because that's what you have to make planets out of. So our planets in our solar system are thought to have formed in one of these rotating disks around the young sun. So our project from cores to disks is to try to study this process from the stage of the cores all the way to the early stages of the disks. There are other programs that are then following that further to even older stages.
The other program, focusing on the evolution of planets, was called FEPS.
FEPS stands for the Formation and Evolution of Planetary Systems. The formation and evolution of planetary systems captures the overall goals of our program in that we are looking at stars that are very much like the Sun and at different ages in their evolutionary paths in their lives as stars in the Milky Way galaxy. The formation aspect is really trying to study the formation of planets and trying to explain our own solar system and understand a bit more how the planets came to be and how common they might be around stars like our Sun and the Milky Way galaxy. And the evolutionary component is in that we are looking at these stars as a function of age and trying to trace out the diversity of planetary evolutionary paths of planetary systems. Our challenge now is to look at what we have from the solar system record and compare it to observations of other stars out in the Milky Way. The real challenge of a program like ours is to take many stars like the Sun at different evolutionary phases and try to string them together to create a movie or an evolutionary picture of how one set of objects might have evolved into the other and eventually resulted in something like our solar system at 5.4 billion years that we see today. Our program is roughly 330 sun-like stars, a very narrow range of star masses focused on the sun. And we are studying them at age ranges that are spaced equally from 3 million years old all the way up to 3 billion years old. We focus in more on the younger phases than on the older phases because that's where most of the action is. Within the first few 100 million years is when we think the planets form. So we have roughly 50 stars in age ranges that are factors of 3. So 3 to 10 million, 10 to 30, 30 to 100, and we focus on about 50 stars in each group. Our goal in the program is to measure the distribution of gas and dust in those systems as a function of the radius in the disk and as a function of age. What we have started to see in our database from Spitzer so far is that the younger systems tend to have more massive dust disks spread out over a larger range of radii in the disk, and we infer that from the temperatures of the material that we see. It seems as though the disks are evolving from the inside out, in that at the early phases you start to lose material in the innermost radii, and at the older ages it's more common to still see material at the larger radii. And a good example is our own solar system, in fact. So if we were to observe our solar system from afar, we would see an outer belt of dust, a large evacuated region, and an inner belt of dust, a very clear signature. We have a model for how we think our own solar system evolved, how its dusty production evolved in time, and we have estimates of what it might have looked like were we able to observe it at an age of 10 million years, 100 million years, 1 billion, and so on. And that is the model that we are benchmarking our data against. We have 50 objects in each age range of interest, and we're trying to look at not just the mean behavior of sun-like stars in those different age ranges, but also the range of possible behaviors. And we're using our model of our own solar system's evolution as a guide. Our ultimate goal is to understand whether our solar system was common or rare in the history of the Milky Way galaxy.
From the deepest reaches of space-time to the dusty beginnings of solar systems like ours, Spitzer has built a legacy of new information that for years to come will help us reveal the secrets of a hidden universe.